Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings. I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. We left off where I was going to show a diagram of simple harmonic motion, because as we previously discovered, the motion, the betatron motion of those protons as they circulate around the synchrotron, it can be described as simple harmonic motion. So I'm going to bring up that diagram. Okay, here's that diagram. Now, think of simple harmonic motion as the motion of a spring, right? Bouncing up and down, okay? That's what simple harmonic motion is. It's a periodic motion. It repeats itself. And when I talked about the force constant, K, in those four equations of motion, right, that we got for the protons as they circulate around the synchrotron, that force constant, K, think of it as the strength of the spring. The bigger K is, the more that spring is compressed and it's gonna vibrate, right? And the smaller the K is, the more loose that spring is. It's not so tightly compacted, okay? Now, you remember we talked about phase space. That's the space that's perpendicular to the proton's trajectory through the synchrotron, okay? The z-axis, all right? And we represented that perpendicular phase space by the x-axis and the y-axis. The x-axis being the horizontal distance of the proton with respect to that central z-axis into the page, and the y-axis, which represents the vertical displacement of that proton with respect to the central axis. So here you have the spring on the left hand, right, bouncing up and down, and you have that same position of that block in phase space, perpendicular to the z-axis trajectory of the proton, okay? You can see how you have deviations to the left, to the right, up and down. Okay, so again, simple harmonic motion, the betatron oscillations of protons as they circulate around a synchrotron. All right. I think that's a great example to show physically what betatron oscillations are doing, okay, with the protons, okay? They're like little springs going back and forth, up and down, around that central trajectory through those quadrupole magnets, okay? All right. So now, again, remember, quadrupole magnets have a physical dimension, a width, a height, a length. So very important to know how to control the simple harmonic motion of those protons, up, down, left, and right, with respect to that central axis as they circulate around the synchrotron. Okay, so now let the pain continue and let's return to my paper. Okie dokie. Okay, when we left off, we had derived the 4 equations of motion of the protons as they circulate around the synchrotron, okay, mathematically, right? And in review, you remember what that took? It took analytic geometry, which is a combination of algebra and geometry. It took trigonometry. It took calculus. It took differential equations. It took boundary value problems, okay? Well, we're about to add another one to the mix, okay? All right, so here are those 4 equations of motion. X, Y, X prime, and Y prime. And if you remember in phase space, right? Remember what we just showed? You had the spring, and then you had the orbit of that same simple harmonic motion represented. X is the horizontal displacement of the proton with respect to that central axis. Y is the vertical displacement of that proton with respect to the central z-axis. And here's that diagram that I drew to represent that. And then the X prime, Y prime, that represents how fast that horizontal and vertical position, how fast those are changing with respect to that central z-axis, not with respect to time. Remember, we wanted to transition from the dependence upon time to the dependence along that vertical axis. And as we're introducing these different mathematical tools, think of having a toolbox, right? You got your hammer, screwdriver, clamps, forceps, right? Tape measure, okay? You have different tools. That's what these mathematical tools are. There are toolbox that physics uses to try to get a handle on the amazing phenomena that occur all around us in nature. Okay, so back to this. All right. So we got to this point, okay? These 4 equations of motion that allow us to identify at any time where those protons are and how fast their positions are changing with respect to the distance around the synchrotron. Here comes another mathematical tool. So let's open up our toolbox, okay? We've used the hammer. We've used the screwdriver, tape measure, okay? Other tools. Now we need another tool. That's called linear algebra, okay? And in linear algebra, you use matrices to describe physical phenomena, okay? Matrices, all right? So let's go down right here. This is a matrix equation, which is equivalent to these four equations of motion, okay, up here. X, X prime, Y, Y prime. These are our four equations of motion expressed as a matrix. As a matrix, okay? How cool is that? All right? And you can see the different elements of our four equations of motion in the matrix, okay? You can see that. All right? You have cosine of the square root of k. You got cosine the square root of k. All right? Now, the quadrupole magnets, and there's 48 of them in the booster synchrotron at Fermilab. 48. And you have one quadrupole magnet that will, with this magnetic field, it will focus the protons along the horizontal direction, okay? But at the same time, it's going to defocus them in the vertical direction, okay? That's how magnetic fields work, magnetic force, okay? On the one hand, they're horizontally focusing, and on the other hand, they're vertically defocusing. And as you might expect, there's quadrupole magnets that will focus in the vertical direction and defocus in the horizontal direction, okay? A lot of symmetry going on here, right? So, what do you think? To keep these protons collimated, you got one quadrupole magnet that's going to focus horizontally and defocus vertically. And then you got another quadrupole magnet that's going to focus vertically and defocus horizontally. So to try to get that collimation, and you know I want to use that word, to get that collimation, you pair them up. You put them together, right? That's what you do. Okay. Here you have two quadrupole magnets together, all right, at Fermilab, right? One is radially focusing in the horizontal direction and axially defocusing in the vertical direction. And then the other one is vice versa. It's axially focusing in the vertical direction and radially defocusing in the horizontal direction. So you put the two together, okay, to get that collimation. So, being that there's 48 quadrupoles in the booster synchrotron at Fermilab, you got 24 cells, each cell consisting of those two types of quadrupole magnets, okay? That's what we have. So, mathematically, we have to try to use matrices to describe those two different types of quadrupoles in those 24 cells, okay? All right.